My name is Zhenming Liu. I'm a postdoc researcher working with Mengxiang. My research interest is streaming algorithm and machine learning for big networks. Today, I'm going to talk about our project on community detection for social and biological networks. In a community detection problem, we are given a social or biological network. We want to find a way to group the nodes so that the nodes in the same group belong to the same community. This problem is important because it has a wide range of applications. For instance, in the context of social network, service providers such as Facebook may be able to use the community detection algorithm as a way to segment the market. By doing so, it will be able to place more accurate, personalized ad to the users. In the context of protein-to-protein network, finding a community usually corresponds with finding proteins that synthesize a specific kind of cancers. Finally, fundamentally understanding the formation of the communities are always an interesting problem to the sociologist. Next, let me briefly talk about the general requirement for the design of a good community detection algorithm. And then there's also a set of specific requirements for our own project. First, a good community detection algorithm should be able to output communities that are intuitively good. Second, the algorithm should be computationally efficient so that it can scale up to process large-scale networks. Third, we should be able to use the algorithm to reason about the formation of the communities. In other words, we want to be able to talk about the confidence interval, the p-value of the output of the algorithm. We also have a specific requirement in our own project. First, we are only interested in finding a specific community in the whole network. In other words, while most of the community detection algorithm focus on finding all the communities over the network, here we are only interested in finding one of them. Second, we also want to be able to incorporate prior information in the algorithm design. For instance, imagine Facebook wants to design a community detection algorithm today. Beyond the social network data it owns, it also has access to other types of data, such as what the users wrote on their wall, or what kind of photos the users like. We believe it's important to leverage this kind of information in the design of a community detection algorithm. Finally, we want to be able to explicitly address the trade-off between false positive and false negative. Next, let me explain our model and our result. We start with a graph that is generated by stochastic processes, such as Endosh-Renyi random graph model or Kleinberg's small word model. Then, the nature or the adversary chooses the community we need to detect. In this example, the red nodes are the community we need to detect. The only constraint we impose over the adversary's choice is that the subgraph induced by the community member needs to be connected. We also observe signals associated with each of the nodes. All the signals are Gaussian random variable. When a node is not a community member, then the signal is sampled from a zero-mean Gaussian random variable. Otherwise, the signal is sampled from a positive mean Gaussian random variable. In our community detection problem, we are given the network structure as well as the signal's value. Our goal is to recover the community decided by the nature. For instance, in this example, if we are given this graph and the values of the signals, then our goal is to recover the red nodes displayed in the previous slide. Our main theorem is a positive result. Specifically, when the graph is sampled from Endosh-Renyi graph or Kleinberg's small word model, then our community detection problem essentially reduces to a problem called the price collecting Steiner tree problem. Then we can use the existing standard algorithm for solving the Steiner tree problem to solve our community detection problem. It turns out this type of algorithm is already used in practice, and this algorithm is highly effective. But people don't know why this algorithm works. We can interpret our positive result as giving a sufficient condition on why this algorithm works. Specifically, when the graph is sampled from Endosh-Renyi random graph or Kleinberg's small word model, then the price-collecting Steiner tree algorithm is guaranteed to output a set that is very close to the community chosen by the natural, with high probability. This is so much of my brief presentation today. If you want to know more about this work, you can read the full version of this paper, which is recently accepted by AI Stacks this year. Thank you.